was quite funny. I was then invited to Nvidia and had the chance really to visit the office of Nvidia at that time. It was a great excitement for me. Yeah, and then picked me up. By the way, I can also post later a YouTube link to this, maybe so that you can see what the application looked like. Yeah, and afterwards, then I always knew that I wanted to do artificial intelligence. At the time, it wasn't that big of a hype as it is today, and everybody thought neural networks is like we were in the winter still. There was no ConvNets dominating ImageNet competition and so on. Yeah, but then I got into basically starting a startup called Xamla, and we created like a machine learning software as a service application. And in this context, I had then, of course, like did a lot of. I had a contact to Torch. At the time, it was Lua Torch, and we later pivoted to robotics. And in this time, I was very active in the Lua Torch development also, because we use Torch basically for everything. Because in robotics, you have point clouds. So I extended the point cloud library and built wrappers to Torch tensors and stuff like that. And this led then to the fantastic opportunity. At the time, I didn't know what would happen, but I rewrote basically all the interfaces to the Torch kernels at that time to make them easier accessible from Lua Torch, from LuaJIT as their foreign function interface. And that also turned out to be a great basis for PyTorch, actually. So this then became, so my part for like foundation of PyTorch was basically to have all these existing kernels in a form which could be like C imported and be easily used from Torch from Python. Yeah, and this also got me then on the PyTorch paper and to with Adam and Saumith and so on. So like meeting all these great people, this was so super exciting. A very small team at the beginning. We were very efficiently like hacking on this, and of course we had no idea to what would come of it. Out of it, that Meta would put so much resources into it, and it would become the greatest machine learning framework which is around. Yeah. Okay, so that's basically a little bit my story. So currently, why have started now CUDA mode? Or like I've asked. There was a conversation between Mark and me. Mark approached me, and we were in a conversation, and we came to this idea to create the CUDA mode. For me, the main motivation was I started now a new job at Aleph Alpha, and a startup, deep learning startup, in AI startup in Germany. And for this, as I'm working as an AI engineer, and I need to be like pimp up my my CUDA knowledge, refresh everything a little bit, and bring me to the latest on this. So this is my personal motivation. Maybe I can now give before I talk the whole full hour, over to Mark, and he can introduce himself maybe first.
Thank you, Andres. Yeah. So hey everyone, I'm Mark. I like for the past like 3 years or so of my life, like I've been working on PyTorch. Most of like my interest like there has been like around performance. Like I think historically, PyTorch was great because it's easy to use, but PyTorch was not so great because it was slow. And so there was like a lot of work done to make it faster, like via compilers. And this is like something I've worked on a lot and written a lot about and tweeted about and etc. So sort of like my interest for like this CUDA mode group, and really it's going to tie back to what the topic of the first lecture is that I've noticed that like at a lot of like these really top like AI companies, they're sort of like the CUDA expert, right? Like this is sort of like the person, like with the dark blinds. And they never go out and they make like a few $1 million a year because they really understand like some deep things about CUDA. So generally I don't like these stories. Like I would much prefer like if people tell me something is really hard, I usually just get angry and I want to learn it out of spite more than anything. However, like I can say that like one sort of uh, like very immediate immediate reason this was I noticed this was useful was like when we were working on some of the examples for things like GPT fast and SAM fast. Writing a custom CUDA kernel just when you needed to ended up like being like a big component of like the secret sauce. Uh, so I guess like without further ado, let me just get started with the talk. If you have any questions or want to interrupt me, feel free to message something in chat. And then Andreas or Thomas can just like call you up. So I don't mind interruptions. So yeah, let me just share my screen. And if everyone can see it, let me know. Can everyone see this?
Yo, perfectly.
Okay, excellent. All right. So yeah, like I said, like I mean, just like some logistics before we get started. Like our host, like the host for this series is going to be like Andreas, like Thomas, and myself. We still need to figure out like the actual like nitty gritties of the schedule, but what we're suspecting is something like one lecture every 2 weeks or so is probably something like feasible. And the kind of content we want to cover is going to be one, what I would call like something like more textbook heavy. So the textbook we're going to be using is this book called Programming Massively Parallel Processors. There's going to be other sessions that are closer to pair programming sessions, so much more applied. Like this one is an example of that. And then also like special projects, like basically if you're listening or if there's like someone who does interesting stuff like in the CUDA space, like we'll be sure to invite them so they can come talk about this. So the target audience, like I have in mind, at least like for this talk, is like Torch programmers that are tired of CUDA tutorial hell. So what's tutorial hell? Tutorial hell is when you're just like reading one more tutorial with the hopes of getting started, and you're reading and reading and reading, and it just feels like you're spinning in place. So there's a real reason, in my opinion, why people get stuck in CUDA tutorial hell. One reason is that like there's sort of like a lot of terminology you need to learn up front. Like basically you have to learn how a GPU works and like its terminology, its programming model. You have to like learn C or C++, which is maybe not something you're actively doing as a PyTorch programmer. So there's that. And then the other aspect is that because that takes so long, people also don't have like a really good idea of like, well, given a PyTorch program, how can I like actually plug in like my super secret spicy like CUDA kernel here and actually get it to work? And how do I even know that my problem will likely be solved by some custom CUDA kernel? So this is really like my intent for this lecture. So the book I mentioned here, Programming Massively Parallel Processors, it's fantastic. Like it's sort of the book. I went through a lot of books. A lot of them were not very good. This one is really, really good. The way you need to read this book is you need to read it and then you need to do all the exercises at the end of the chapter. If you can't do the exercises, it really means you just did not understand the chapter, so do it again. So highly recommend you do this, and we'll be going over like the first like probably like 11 or so chapters of this book during this series. But for different kind of content, like if you prefer like YouTube talks or if you prefer like blogs or so, we have like this resource stream channel, like GitHub repo that Andrea started. All the communication regarding like our scheduling or projects or what we're thinking about or Q&A about the content will happen here on this Discord channel. And all of the sessions we'll have will be recorded. So like we just created a new YouTube channel called CUDA Mode. It has like no videos on it. So this will be the very first video that we'll be pushing out. So yeah, like basically, like I said, the goal for this lecture is how can you integrate a custom CUDA kernel in a PyTorch program, and then how do you profile it? All of the code I'm covering is in this like GitHub repo called CUDA Mode Lecture 1. I need to clean this up and we'll add it to the CUDA Mode org later. But generally, like my attitude going over this content has been kind of like this. Like so, this is me when I'm programming. Like essentially, like I can't understand things like very quickly, and if I read a lot of terminology, I just get lost and eventually get discouraged, and we'll go do something else. However, like with profiling, I can sort of very visually see and understand things in a black box way. So I don't really need to understand all the details about how a GPU or CUDA works to be able to do useful stuff with it. So this is like the perspective I want to impart. Okay, So the first thing we're going to start off with is this simple example here. So I have this example here of, here, where was it? Here. So I was sort of curious, like in PyTorch, like let's say I want to do an element-wise square. So what an element-wise square is, let's say you have a matrix, you go over every element and you multiply it by itself. So this is an example of a point-wise operation. Point-wise operations are really important in machine learning, like things like softmax are examples of point-wise functions, like sines, cosines, like there's sort of like a lot of functions that fall under the point-wise setting. And I was sort of curious, like, okay, well, I'm going to sort of compare torch square to multiplying a by itself to doing like doing like this power of 2 operation and then seeing what's faster, right? So the way I did this was like the first really key thing to remember about profiling CUDA, and really the main, like maybe the most important thing you can ever know about CUDA is that CUDA is async. As in, if you were to just use the Python time module, you're just going to measure the overhead that it takes to launch a kernel and not how much time the kernel actually took. So this is a function like I wrote this to show you how to do this. Like basically, you have like you basically set up like a CUDA start event and an end event. You need to do a warm-up because the first time you call CUDA in a PyTorch function, it's going to initialize the CUDA context. So that's going to distort your measurements. So that's why you need like some sort of warm-up. And then when you're done, you need to do like a CUDA synchronize because again, it's CUDA's async. And then you can get like a, and then you can get like a time value. So long story short, like the profiler that I used here is called the Torch Autograd profiler, right? And then the Torch Autograd profiler's view looks something like this. It's gonna essentially show you like these are all the kernels that are running and like how much time they took on the CPU versus, excuse me? Oh. So this is going to show you how much time these kernels took on the CPU versus the GPU and how much time they took total, how many times each kernel was called. And just like looking at this, like we already sort of learned a few interesting things about even the toy function. So if you see this a10 square here, it makes a call to a10 pow. So a10 is, you can think of it as like, this is sort of like the low level, like C++ like dialect for PyTorch, like these are the individual operations. So we look at this and we know, okay, well, it seems like there isn't really a function called square that does anything. There's a function called pow, and then we probably set its value to 2. And we're like, oh, interesting. So we learned something about PyTorch just like looking at this. We also noticed that like, well, in the case when we're doing a times a, it's not actually doing a pow, it's doing a multiplication operation. And the multiplication is like slightly faster than the power operation, which is interesting. I don't have like a good answer for this, like besides like, multiplication is like a more popular operation, so more people are likely to spend time optimizing it. And then here, like when we use like the Python built-in, it just used a10 pow directly, for example. So great, we already like we don't know anything about like PyTorch internals, and just like running the profiler quickly gives us like an interesting idea of what's going on. So great. So this was the Autograd profiler. And like I said, to use it, you just have like this context manager here, and then you just like run individual operations in it. So like, and then, you can turn this into a table and sort it and look at, like limit to the top, like the most time consuming kernels. So another a bit more interesting profiler is the PyTorch profiler. So what the PyTorch profiler is it's a visual profiler, and it essentially gives you a Chrome trace, and then it's going to be a JSON file, and then you drag and drop this JSON file to Chrome, and once you do that, you can get a view that looks something like this. So we notice like, okay, well, first off, we have like this function here. So looking at the square function, it's split into 2 parts. The first part is like this function called memcopy host to device. And this is like very common CUDA terminology. This is basically equivalent to your .CUDA call when you're sending a tensor to the GPU. And you're going to notice that here, like, okay, well, we have this a10 copy, and eventually it's going to dispatch to this CUDA memcopy async. And then this is going to create like this GPU kernel, memcopy host to device. So you host, like when it says pageable, pageable just means the pageable memory on the host. So you can think of this as RAM, but it can just means it can be freely swapped in and out of RAM. So again, getting the PyTorch profiler working is also pretty simple. So this is what the code looks like. So the easy version of it is you just say something like with profiler, profile the CPU activities and the GPU activities, and that's it. In practice, it looks a bit more complicated because you need like a warm up and schedule and stuff like that. So it'll end up looking like a bit longer. But the actual incantation is as simple as this. And when you're done, you run this function like export Chrome trace, and then this will give you like a JSON file like you can copy paste into Chrome and inspect this. So great. So we're back to our square operation. We're sending we're sending a tensor to the GPU, and after that we need to compute the actual square. And we learn here that like, so here if you look at these arrows, so these arrows are basically examples of what are called flow events in the PyTorch profiler, which means that like this is so what this says, it's CUDA launch. It's basically a CUDA kernel launch. So we see, okay, well, there's this A10 square. It's dispatching to an A10 POW, and then this is gonna launch a CUDA kernel. And now we get something that looks like an actual CUDA kernel, and it's called like vectorized element-wise kernel with like 4 blocks. And we're like, okay, interesting. So now we again learned something about PyTorch where the way they do like square operations over like this size of matrix that we have is with 4 blocks, cool. But the problem with this approach too is that it doesn't necessarily give us like any idea of like how fast is this kernel or what we could do better with it. It just tells us like the name of the kernel. So a lot of these kernels you can actually go to the PyTorch repo and you can kind of see what they look like. So this is an example of like an element-wise, like the element-wise CUDA kernel. And you can like go over this and see what it looks like. There'll be like a whole bunch of these. So basically, if you go here and like type in like .cu, there's gonna be like at least like 40 files here of like different kinds of CUDA kernels. So they're like also like a good educational tool, just so you can see, instead of looking at a kernel from a textbook, like look at a kernel for like more ML-ish code, it'll resonate more with you. So here, okay, like this, like the sin, cosine, stuff like that. Anyway. All right, so back to sort of the first main question we had, which is how do we actually integrate a CUDA kernel in PyTorch, right? Like one problem is that like CUDA in general is typically written using C or C++. So how do we load a C++ function within a PyTorch program or like a Python program more generally? So one way to do it is what's called PyBind. Like basically you essentially create like Python bindings for like a C++ file. This is a bit annoying to do, or, the easiest way, and this is like, sort of like my promise, the easiest way to do this is with this function in PyTorch called load inline. So the way this function works is that you pass it in a C++ source file. Like here, I'm passing it in as a string, but this could just be like a path to a file or whatever. And this is just like a hello world function. So what we're going to do is we're going to say, okay, well, like we have like this one function that we need to expose called hello world. And then once I load this module this way, I can call it. So I can say like my module hello world, and then this will return hello world to my console, even though this is a C++ function. So what's really cool about this is that you can actually see what this does under the hood. Under the hood, this is going to create this temp directory, and you're going to have a function called main CPP. So you see here the hello world, and then it'll show you the PyBind function for it. So this is great because if you're trying to learn how PyBind works, this is way better than a tutorial. Just write a toy C++ program, and then you can see exactly like how this works here. And then the second thing it's going to create is it's this build.ninja script. So again, writing make files is like very hard. So this will essentially code generate like the equivalent of a make file for you. And you can come in here and you can see, okay, well, there's this build function and it's going to run this compile thing on this main CPP file. And okay, and then it's like running like this compiler, like with these compiler flags, and then it's gonna have an object file out, and then this object file is called out. So again, this is just like a really great way to learn, and you don't need to write all of this. Like this is really annoying. Like you need to come in and say, let's look at some stuff here. Like you need to put a path to like the PyBind module and iSystem, and you know we don't care about any of this. Like all we care about is calling a C++ function. Learning about build systems is just like not the most interesting thing in the world. And so that's why I highly, highly recommend this load inline function here. Great. So this is for like a general C++ program, but let me show you what a Python what a CUDA program might look like. Oh yeah, what a CUDA program might look like. So let's say we have this program instead. And again, like here, what we're doing is we're doing our element-wise like matrix multiplication. So there's two ways of like going about this problem. We could either have like a row and column index, and then basically get like a single index from them. Like essentially, you can imagine that like you can turn a matrix into a vector, like linearize it, and then go over every element and multiply it by itself. So this is what this operation is doing here. So this is an example of a CUDA kernel. So this is the actual kernel itself. But then we're also going to have like a wrapper function that will turn PyTorch tensors and put them in a format that like this kernel expects. So this is like what this wrapper or driver function might look like. And then the actual C++ function that you need to expose in your main.cpp looks closer to this. Like it's just going to be the name of the function and it's just going to call it. So this is really great because like now when you're saying load inline, what you can do is you can have like a path to your C++ file and a path to your CUDA file. You can also pass in some extra CUDA flags. So O2 typically means like compiler optimizations. And then we're going to say like, okay, we're going to build these functions here. And then same thing, like now we want to call this function, like let's say we have we called this module the square matrix extension. So we can just say square matrix extension, square matrix, which is now Python over A. And we can basically get the square operation that we expect here. So again, like learning how to build a CUDA kernel can be annoying. But if you look at like what this code generates, is it'll code generate a CUDA file. So this is the .cu file. And it's going to be exactly the string that I showed you earlier. There's going to be the main CPP function. And the main CPP function here is gonna basically PyBind this square matrix. The interesting thing here is I also remember in our code here, we didn't actually, let me show you here. Where was it?
Oh yeah. One question was, if you now do this inline mode, and so is this folder which you show with the generated source code, is it automatically always generated, and can you look at the output, or is it normally behind the scenes? And also, how long does it take normally to if you do inline compilation?
Okay,
like normal.
Yeah, these are great questions. So I was going to cover those in a second. So let me go back here. No worries at all. So basically here, there's this parameter. Let me load inline here. So this is not invisible because you can just set this directory called build directory. And the thing I'm showing you here is actually what this code generated. I didn't write any of this, just to be clear. So this is all code generated by the load inline function. So that's one. The second thing is that like how long this takes. Well, again, it depends on the kernel. Typically compiling a kernel online, it takes a while. That's why like building PyTorch from source really sucks. That's why like building flash attention from source really sucks, because you're going through all of those kernels and building them one by one. So that's expected, but this is just kind of like the easiest way to get started with this. The good thing about this is that like you don't need to do this over and over again, because like once you load inline and if you know how to call these things directly, you can just go ahead and do that. Like you have like all of these kernels, but like I'm really just now more optimizing for like you getting started, I guess. And so that's why I'm not necessarily showing how to like cache these compilation artifacts or anything of the sort. Yes. Okay. So that's pretty much like how you can go about, like you have a custom CUDA kernel, you want to use it in PyTorch, use load inline. It's a bit finicky to get right the first time, so I would just suggest like go over like my example and like adapt it to your needs. You'll get everything you need. Okay, so another way potentially of integrating, like, okay, so right now we just took the path of I wrote some C or C++ code. I want to integrate it within my PyTorch program. That's kind of annoying, so we needed to use like load inline. An alternative is just to write Python code. So basically, like, let's say we use something like Numba. And conceptually, this is exactly the same thing. Like, you know, there's some boilerplate that's a bit different, like setting up the grid. But conceptually, it's the same thing. Like, we basically have a result matrix, and the way we go over every element in like the input matrix, and we square it by itself. And then, you know, we have a to device instead of to CUDA. We have this device array. So the terminology is all slightly different, but conceptually this is very, very similar to the way you would program regular CUDA. So you use whatever is comfortable. I think for the purposes of this class, we're not going to use Numba. At least I won't use Numba. We'll either use like C or C++ or Triton. So let's talk about Triton for a second. All right. So Triton is also like another example. So Triton is a DSL. It's not like is a DSL in Python, and it doesn't generate CUDA. So it's not like you run this program and it's going to write a CUDA kernel for you. It's actually going to generate a PTX kernel, a PTX code for you, which is basically the CUDA assembly. And I'll show you an example of what this looks like in a second. But again, integrating this into a PyTorch program is trivial because it's a Python function. So you just call a Python function from your like an n forward function, and there's sort of like nothing crazy you need to do. So this is like an example of a square kernel like I wrote, and I wrote this in Triton. Like this is like the first, you know, somewhat interesting kernel like I've written, and I wrote this and I ran the experiments on an A10G, and I noticed that like my Triton code was actually like a bit slower than the code that's already in PyTorch. So basically my custom kernel was slower than torch.square. This is not great because a slow CUDA kernel is not useful. Like the reason why we deal with the complexity of CUDA and the prices of GPUs is for performance. So you really have to have like this like very like performance first mentality when going about it. So I was like, okay, well, you know, like I don't know what's going on. I tried torch compile as well. So what was interesting to me is torch compile actually also made the performance worse. And it made it mimic closer the performance of Triton because torch compile will generate torch compile will generate OpenAI Triton kernels. And I was like, like, okay, there's like something interesting here going on. So I was like, well, you know, maybe this is something specific to an A10G. So I ran this on a 4090 and I got like very similar results as well. And here I was like, okay, crap, like well, what's going on here, right? So how did I go about debugging this? So first off, let me show you my kernel quickly. All right. So conceptually here, like it also looks like very similar, where like the sort of interesting part of it is like, well, you have this row, and the row is like you're loading from input pointers with like an offset. And then
is it possible to make it a little bit larger if you're in browser? Yeah.
What about now?
Great.
Yeah. Yeah. So basically it like so first off, like here, like if you look at this kernel, also conceptually, it's very similar to the CUDA kernel I showed you. The sort of interesting part is like the sort of three interesting parts are you have like this, like we're basically loading things row by row. Like we're loading one row at a time into SRAM, and we then take this row and multiply it like by itself, and then we store like and then we store these output pointers, and then we write them back out to like global memory. So conceptually it's all similar, but instead of like operating over threads, we're operating over rows. And the way I adapted this was like I just took a tutorial that they already had for where was it? Let's see here. Yeah, like basically the very first tutorial for Triton is this guy. It's like this fused softmax operation, and they do something very similar to what I just showed you here. But then like when they ran their results, like they were obviously like much faster than Torch JIT or Torch Native. And so I was like a bit surprised. I was like, well, what, like, you know, conceptually they're both like pointwise ops. Like these things should behave similarly. Like, well, what's going on here, right? So back to here. Okay, so my suspicion after profiling a bunch, and I'll go over the profiling tools, is that it's just like that my kernel launch parameters were really bad. And so I just fixed the block size in my code here to 1024, and then this made the results look closer to this. So it was just like a complete like reversal of the trend. But there's profile, and I'll show you now like the profiler tool that will help you do this kind of stuff. All right. So another thing I want to mention about like Triton is Triton has a debugger now, and it's great. So basically, if you come here, you can say like Triton JIT interpret equals true, and then you can just literally add like a Python breakpoint, and then you can inspect this code like line by line. Pretty much everything that you see here is going to be an object of type wrapped tensor. So if you just say like whatever, like if you print the variables dot wrap tensor, you can actually see basically what a program ID looks like, what a column offset looks like. Because Triton is like a block-based programming language, and the alternative to this is that you would need to write your kernel line by line, load whatever you want, and then print it from your driver program. This is very annoying and very slow, so highly recommend the new interpret mode.
This is so awesome, incredible. This Triton debugging feature is something I've been looking for so long. Yeah,
it's not documented anywhere. There's also an environment variable. I think it's like Triton underscore interpret equals true or something. But it's fantastic. Like the fact that you can just use like a regular Python breakpoint for me as an educational tool has just been fantastic. Like for what it's worth, like actually, like let's talk about this for a second. Like let's say you tried to add like a print statement here, like this is like gonna crash. Like it's just like you cannot add print statements. Like this is just not something that exists in the language. You would again, like you have like variables, you store them to global memory, and then only then can you read them. But like as the CUDA kernel is running, it's actually like a black box, and this is debugging mode is sort of like a significant step forward in usability, in my opinion.
Question: when you run it with the debugger, do then the kernels still execute in parallel or sequentially?
I'm not sure how it works under the hood, but I have a friend Zahi who works on the Triton team, and I'll ask him. If you don't mind asking me the question as well in chat, like I can make sure to follow up on that as well.
I think even if it's not like fully like optimized, the real kernel running in that moment, just to get the state feedback. I know of earlier versions, like very early versions of Triton, they also allowed printing, like during the first compilation or something when the Python was evaluated. I don't know how exactly it would work, but it allowed printing. And if you have now something similar which allows us to inspect what's going on there, because it's so easy to make some index errors or whatever, and just I think it's super great feature.
My solution until now was to just like crash the kernel, and then I would get all the information.
It's a cool approach. All right. So what the cool thing about Triton as well is that when you're running a Triton kernel, it's gonna like it has a cache called .triton where it will actually store all like basically Triton, like a big chunk of it is like it's leveraging like LLVM quite heavily. So you can go to an individual folder and look at all the individual IRs, including the PTX, right? And I've often heard people say like, oh, you don't need to learn PTX or whatever. I feel like it's quite useful. So let me sort of give you an example here. Like this is the actual square kernel, like this is all the PTX for it. It seems long, but it's actually not too bad. The important part is here. Like basically, remember what we're doing. We're doing an element-wise like matrix square, right? And then here we notice, like there's this mul, and we're multiplying f1 by f1, and then we're storing it in f9. And then we're doing this up until f8. So that means that Triton is effectively leveraging 8 registers at a time, and then to have like for the input values, and then using like another 8 for the output values. And for me, this was interesting. Like I expected, to be frank, a lot more. I was like, well, I heard there's like, I don't know, maybe there's like a lot more registers that it uses, and why isn't it using more or whatever. So this was interesting that it's doing it 8 at a time. The other thing that's interesting is that, where was it? Here. So you'll notice like parts of the program here, like for example, the store global. So this is like us like writing the variables back to global memory. So if part of the kernel is using shared memory versus global memory, you can see what are the actual registers for this, like directly like looking at these PTX kernels. And then there's also, I think TID, yeah. Here, and you can also see things like, for example, oh yeah, like the thread ID, for example, is stored in this like register called R25. Like we're loading like these, like so like these are like the kernels we're loading. So it's actually like not too bad, and you can what you could do, like a trick I like to use for reading assembly, is just copy paste this whole thing into ChatGPT, and you can ask it to like add annotations for you. It's like really quite helpful as you're ramping up on PTX. Yeah. So another trick is that, like, remember, like what I did was like I was writing this like square kernel myself, but instead of like writing a kernel, you could code generate it yourself. So so spoiler, like I work very closely like with the Torch compile team on PyTorch. So there's this one flag. So basically, I basically have a program where it's basically import Torch. Torch compile, Torch square, and then I basically add, instead of just calling this like Python compile square, I also add this environment variables called Torch logs output code, and it'll print to the console the actual code that Torch compile generates for this kernel. And so again, this way you can, instead of learning how to write a Triton kernel, you just write your PyTorch program, get a Triton kernel out, look at it, and use that as a starting point that you can optimize and learn and change stuff around. So the interesting thing you'll notice about like this program is that like one, they're not operating like row by row in the way I was like doing things. Like so, like the code is actually much simpler. But you can see here, like they have this temp1, and then temp1, you're multiplying like a value by itself. So this is like the element-wise like matrix matmul here. You can also see that like it had like some heuristics, like for example, that these are like FP32, like this is using FP32, so you could make this use FP16 or BF16 or whatever you want. It also passes in some compiler heuristics, like the number of elements. So this helps to sort of like do like auto-tuning heuristics as well. So I thought this was like pretty cool. So like for sure, like if you're getting started, use this mode. Like write like really toy, like 1-line, 2-line programs, and you can see how this goes. So one example that I'm not showing here is like the most important optimization it ends up for a lot of machine learning code tends to be fusions. And what fusions are, like from the perspective of a kernel, is it basically means you're having more and more things be in a single kernel. So here the kernel is called Triton _, right? So this is actually the kernel name that you'll see in a profiler. And like, let's say we're running the square operation twice, we expect to see like a temp1 and then a temp2 equals temp1 times temp1. And this is basically would tell us and confirm to us that indeed things are being fused here. Yeah. All right. So this is like as far as like integrating and generating these code examples go. I want to now quickly talk about the most useful CUDA profiler I've come across. And it's called the Nvidia Compute Profiler, like NCU. And the way to use it is basically you just say NCU python train.py. I'm going to warn you from now that this doesn't work on the vast majority of cloud vendors because they won't give you this profiling information. But if you have your own like dev GPU, like your own like GPU at home, this works great with like with no kinks. And the logs like look something like this. Like, so this is like the written logs. And it'll show you, for example, like, okay, well, this is like the L1 cache throughput, the L2 cache throughput. It'll tell you, oh, like it seems like this kernel has low compute throughput and memory bandwidth utilization relative to the peak compute. And it'll give you percentages. So basically it'll tell you, hey, like you're like at 60% of the peak. So this is pretty good because this gives you like a good like roofline thing to target. Like it's gonna give you like, let's say 2 tips, and it tells you, hey, if you do more work here, you can get maybe 40% here, 30% there. And so this gives you like a good target for you to figure out like, is my kernel actually running quickly or not? Like that way you know like what's sort of like theoretically achievable. So for example, like the most actionable hint here was like this one. So it'll say the kernel grid is too small to fill in the available resources on this device, resulting in only like 0.4 full wave across all SMs. Look at launch statistics for more details. So like understanding the details of this is kind of like an example of like, we just need to go through the textbook together. But from like a practitioner's perspective, you know, you have your kernel that you're launching, like make it bigger. Like pad your inputs, right? So this gives you like concrete things that you can try out and then try them out, see if the perf changes, and then move along. And then, you know, sort of learn like the basics of CUDA like as you need them. So NCU also has like a very neat like visual profiler. So the only difference is you need to say like -- set full -o, and then the view will look something like this. So here, for example, like this is running like here, like it'll show you like a kernel, like what's the memory throughput, the compute throughput, the block size, etc. One thing I thought was kind of interesting is that like, so like let's say in NCU, they'll say some things like here. So for example, here it gave us 3 actionable hints. It told us about like you can improve your tail effect for 50% speed up. And then you have your achieved occupancy and long scoreboard stalls that can each, if you fix those, that would be probably like another 20% speed up. Okay, great. So the tail effect and achieved occupancy are often controlled by things like padding. So padding you can control, but then things like the long scoreboard stalls, these are things where you need to either coalesce your reads and writes and use shared memory. But this is controlled by Triton. Right? So the reason I say this is because you wrote a Triton kernel for something, you got this trace, right? You can get 70% speedups if you pad things. So this is within your control. And you can get potentially a 20% speedup if you think you can do a better job than Triton at doing shared memory management and memory coalescing, right? So it gives you like a very natural time to decide to upgrade from Torch to Triton to CUDA, as opposed to just going in like with CUDA immediately and like mucking around and, you know, writing something that would be slower than something than the Triton autotuner. All right. Yeah. So another view I quite liked was this one. So basically here, like this is like back to the, so this will show you the, like this is the Triton kernel. And then it will show you, for example, here, like on this TL load, like these are like global reads. So you're like, okay, well, there's like a lot of global reads here. And then you can look at the PTX and it's again, remember when I said this is the R8 times R8 gives you R15. So like something similar is happening here, but instead of like having 8 registers, it seems that we only have 4 for whatever reason here. And then you can basically look at your individual lines of code, change them, and see effectively what you need to change to get better perf. All right, and that's pretty much like all I had. Like I think the main thing the main important lessons from this is that it's really easy to integrate a custom CUDA kernel in PyTorch with load in line. Integrating Triton kernels is really easy. You know, in this order, start with the Autograd profiler, then the PyTorch profiler, and then NCU. And doing that should get you like basically get you good enough at CUDA to write things like, you know, GPT fast or like SAM fast. And then obviously, like as we go along in the course and learn more advanced stuff, like we'll sort of revisit this and start and all get better. But for now, like these are the main things I wanted to stress on. And so thank you, everyone.
Thank you very much, Mark. This was really awesome. I think we went pretty deep also in some tools, so we probably need to elaborate on some things later. Maybe for now, if you have questions to Mark, you could either ask them directly or write them in the chat. We had, for example, one question regarding the relationship between Triton and Torch compile. Mark, can you say something maybe about this? Do you know what's going on a little bit under the hood? Or
Yeah, sure. It's actually like compilers are quite dumb in the sense that like maybe I can show you. Let me see if I can find the code here quickly. I won't find it like as quickly, but like let's say you have like you have an operation like torch.square that you're trying to run, right? The way like torch compile will go over this, it'll be like, okay, well I have this op called torch.square. I don't know what this is because this is not like sort of a very primitive operation. So instead, I'm going to turn it into like a torch.mul operation, right? So great. So now you have like a torch.mul operation. And literally what torch compile will do is it will read this torch.mul operation and it will write a string to a file on disk called essentially using like the Triton, basically the equivalent of Triton.mul. And then you have a file, and then it's a Triton file, and then you just run it. So like a lot of compilers like work this way. They'll essentially like write strings to disk based on like certain heuristics, and then you run them. And that's kind of like at a high level how you go from a PyTorch program to like a Triton program. Hello?
Mark, can you still hear me? I think something broke at my side. Can you hear me?
Hello?
Hello,
Yeah,
Mark.
I can hear both of you guys.
Okay.
I have
Yeah,
a
I
feeling
can
he
hear you
can't
both
hear
too.
us.
Okay. So great. Mark, I hope you can still hear me.
I can hear you, yes.
Okay. Great. Something with audio went wrong on my side. But cool. So we have like two more questions. I don't know if you can see the chat, Mark. So there was from John Whittaker. Thanks, Mark. That was great. For the compile to Triton trick, how often do you find the code readable enough to be a useful starting point?
I would say almost always because there's not many clever things like basically compilers are limited in the sense that like they can't do things that are too clever. And so like for machine learning code, the main thing that you want to look for is that I want as many things fused into a single kernel as possible, which means I need as few kernels as possible. And so generally taking the Triton code is very readable. The main problem is that like the variable names are just temp1 and temp0 and whatever. But again, like using it as a starting point and adding your own comments on top is a trick I use all the time these days. Whenever I'm writing any Triton kernel, I actually forgot to do it for this example for my Square kernel, but like I said, it's a great tool to get started in this regard.
Okay, yeah, thank you very much, Mark. By the way, do we still have your stream on, or is it?
No, I'm not sharing
Okay.
anything. I can.
Because,
Yeah.
maybe next time we can again go do this a little bit to more detail how this like this trick really works, because it was for some people a little bit too fast. Okay.
So wait. So like, are people? I mean, if people are curious about like the details there, let me see. So wait, first let me just cover the question. So did you compare the performance of Triton versus CUDA for the Square kernel? I did not. And does CUDA also generate PTX code? Yes. I don't know how you can look at it, but I'm pretty sure it's like a quick Google search away. Yeah, so the Triton Square, exactly, yeah. So actually, wait, let me compile PyTorch. Okay, yeah, maybe let's do some live programming then, just because I don't have like a good example for this. So this is like my Windows PC, so I don't have like all of my, I don't have everything here. But essentially the way this would look like for Torch compile, to generate the Triton kernel for it, would be something like this. So let me call this like square compile.py. This is going to be like fully functional code. So I'm going to say define square, and then this is going to be a, and then it's going to be return torch.square a, and then I'm going to say optimized square equals torch.compile square. And then because it's a JIT, you actually need to run it. I'm going to say optimize square, and then like this. So this is actually like the code. Maybe there's a missing parentheses. No. So this is actually the code that you would need to run, and then you just call this with like torch logs equals output code. And then you would say Python square compile. And that's it. This will like as you run this, it'll print the Triton kernel to your console. The main reason this is kind of interesting is because like let's say now like we're doing something like a torch.square. So this is like a single, like this is going to be like a single operation. But let's say we have a program that looks kind of like this. Like let's say we have a equals torch.square a. So we're doing two squares, right? So let's think about this problem for a second. What's going to happen is that you basically need to read the A and then write back to A. And then you read the A, then write back to A. So if you're running this in an eager PyTorch program, you're going to have like one kernel being launched for each, as opposed to just fusing these things together. So if we run this, if Torch compile is doing its job correctly, we would expect to see like this, like two squares happening in a single kernel. Otherwise, like something's going wrong. So this is kind of like the main, this is like a great educational tool to go from PyTorch to Triton.
Super cool. This was like live coding session. I think we need to somehow include this also in future sessions a little bit.
Yeah, I don't know if Luca and Tiga is on the call, but like the Lightning AI Studio is really neat for like this like live coding session, but I still had some issues connecting NCU to it. So I think like once we get that up and running, I think it'll be very easy to do like live coding sessions with all of this stuff.
Yeah, cool. So in general, Mark, how large can the things be with Torch compile? And what would you to understand a little bit, when does Torch compile break? So I tried it, for example, on very complex projects which were written without like this Torch compile thing in mind, and there's a lot of if statements and other things in, and also like for example, flash attention was in there and stuff, and didn't like directly work, I would say. So what would you say? Is it like do you have to write a little bit with this in advance in mind? And
yeah, like so I think the design philosophy of Torch compile is that you don't change your code at all. Like basically like whatever code that you have, it might not be the most performant code in the world, but it'll like it shouldn't make your performance worse by adding it. Obviously, if you write your code with Torch compile in mind, we've had examples of people getting state of the art performance with sort of SAM, Stable Diffusion, and then GPT. So it's certainly possible. So if that's potentially like another interesting future topic for people, which is like, how do I go from a model that I care about to really good perf? Like if this is interesting, we can certainly sort of like have a lecture just like on that, discussing like concepts like graph breaks and like in-place mutation and CUDA graphs. And I think there's sort of like a lot of interesting things we can discuss.
yeah, I think this in a separate session that would be super awesome, because I personally also struggle a little bit to see the difference between all the different options that are available with CUDA graphs with Torch compile, and when do I need, for example, to really write my own kernel, and how to make this decision, basically, how to spend the time best making things fast. And also how dynamic are things, for example, and when are they no longer dynamic?
So folks, I really apologize, but I forgot like a week ago that I have a hard stop at 1. I was hoping we could go for much longer. However, like I think this is good because like I'm happy people found this talk interesting. We'll share more news on when the second lecture is going to be shared soon. And if there's sort of any topics that you'd like us to cover, please make suggestions in the Discord channel, and we'll take a look, and we'll try to either give the content ourselves or invite like some relevant experts that you might know of in the sort of performance space. So thank you, everyone. I really appreciate everyone's time.
Yeah, thanks everybody. This couldn't have said it better than Mark. Maybe one final comment. We also are looking, of course, for others to make presentations. So maybe next week I'll do a presentation, and then also, yeah, we'll have a certain like lineup, which we'll do, like Thomas maybe, for example, will also show something. But after that, we would be very happy also for others to tell a little bit their story about CUDA and yeah, stuff. So thank you, everybody. Yeah, stay around here and